Hello, am I audible and is my screen visible? Can anyone let me know if I'm audible and my screen is visible? Okay, thank you. So, good evening, everyone. Welcome to this NPTEL live session for the NPTEL course Introduction to Machine Learning. My name is Awan Maiti. I'm a PhD scholar in the Department of Computer Science and Engineering at IIT Kharagpur. So in this live session we will discuss some practice problems on week 11 topics. In week 11 Gaussian mixture model and expectation maximization algorithms. These topics were covered in week 11. So we will discuss some practice problems on those two topics, and if you have any questions or queries, please feel free to ask me. So we will start solving some practice problems first, and after that if you have any questions or queries, you can ask me. This is question 1. In each of the options, the diagram contains a log likelihood function for a particular problem as well as the initial value of the parameter used in the execution of the EM algorithm. In which of the given scenarios will the EM algorithm be able to achieve the global maximum? So these curves in the 4 options, these curves are the log likelihood functions for some problem, and we want to use EM algorithm or expectation maximization algorithm to get the optimal value for that problem. And these values, these theta initial values are given. So these are the initial parameter or theta values. So in which of these diagrams the EM algorithm will be able to reach the global maximum point? So these are the initial values of the parameters theta which we want to optimize. So I've already got one answer in the chat. Raghav is saying option B. Okay. Pratik Tiwari is also saying option B. Anyone else? Any other answers? Pratik is saying C can also be the answer. Okay. So the correct answer here is option C, not B. I've got two answers uh, as B in the chat. So we want to find out in which scenario it will be able to reach the global maximum. So for example, in the first option, option A, the global maximum point is here. So if we start at this point, so it will reach here at this point, and after this point it will not be able to reach the global maximum, because after that the slope is negative, so it will not go into that direction and it will stop here. So it will find a local maximum point, but it will not be able to go to the global maximum point, which is here. So for that reason, option A is not correct. And for this similar reason, option D would also be not correct, because it starts at this point and it would go up to this point, and after that the slope becomes negative. So if slope is negative, it will not move any farther, so it will just stop at this local maximum point. So it will also be at this point, it will not find the global maximum, which is here. So D is also not correct, A is also not correct. So in case of B, this is the starting point, this is the initial value of the parameters. So it can either go in this direction, it can also go in this direction. So if it goes towards the right, it will be able to go to the maximum point, global maximum point. But if it follows the left route, in that case it will reach this point and it will not move any further. And this is and this point is a local maximum point, you can see. So it might go towards right, might go towards left. So we don't know, we don't know for sure whether it will be able to give you the correct the global maximum point. So that's why we cannot certainly say that it might give you the correct answer, but we cannot be 100% certain. But in case of option C, we can see that there are no other local maximum point from the starting location to the global maximum point. So it will always be going up, and it will reach this global maximum point and it will stop there, because there is not a single point in this path from this initial parameter value to the global maximum value where the slope is negative. And if slope is negative, it might stop at that point, but there is no local maximum point here. So it will not get stuck into any local maximum point, it will reach the global maximum. So that's why option C is the only correct answer. Option B is close, but not we cannot be 100% sure that it will always give you the global maximum point. But in case of C, it will always end up at the global maximum point. So option C is the right answer. Is there any doubt in this question? Okay, so we can move on to question 2. So for a given GMM model in this figure, GMM is Gaussian mixture model. So this is the diagram. This is the diagram that is given for the GMM model, and the boundaries are also drawn here. So these Gaussian contours are also drawn here. So what is the value of K from this figure? What is the value of K? Pratik Tiwari is saying 4, Mishti Pandey is saying 4. Shankar Lal is also saying 4. Okay, so I've got 3 answers, all are saying 4. Any other answer? Is the correct answer is option B, which is 4. So K is basically the number of clusters in the Gaussian mixture model, or the number of components in the Gaussian mixture model. Components or clusters are same in case of Gaussian mixture model. So from the diagram you can see this is one component, this is another component, this is the third component, and this is the fourth component. So these are the 4 clusters that the Gaussian mixture model has created. So the value of K would be 4. So basically you have to find out how many clusters are there in the final Gaussian mixture model. That would be the value of K. Yeah, so equal to the number of clusters that you can see in this figure. That would be the value of K. Now question 3. This question is also for this same figure here, for same Gaussian mixture model figure. What is the minimum value of K dash not equal to K? So in the previous question we found out K to be 4. So what is the value of K dash which is not equal to 4, for which you will get a very similar density estimation? So basically if 4 is not the answer, then which value of K, or in case of K dash here, will give you a very similar density estimation that you can find out from this figure, from the distribution of the data. Pratik Tiwari says 3, Shankar Lal says 3, Mishti Pandey is also saying 3. Okay. Anyone else? The correct answer is option A3. So we want to find out the minimum value of K dash not equal to 4, which we got from the previous question, for which we will get a similar density estimation using GMM. So this is certainly one cluster that we need. There are no other clusters nearby. This cluster would also be there, and we can merge these 2 clusters into one. So this cluster and this cluster, we can merge these 2 into one cluster, because those 2 clusters are very close to each other. So even if we club these 2 into one cluster, it would still be very much accurate. It will still give you a similar density estimation. So that's why these 2 clusters can be merged into one. So from that point of view, we can find out the minimum value of K dash to be 3, which will give you a similar density estimation in case of GNM. So correct answer would be 3 here. Next question is again on the same GMM diagram. So assume equal pi I is the mixing coefficient, or the probability value for every cluster, for which the Gaussian model after the convergence in Q2, in question 2 we had K equals 4. So 4 clusters we took in question 2. So this was the question 2. So we found out 4 clusters here. So K equals 4. So if we assume equal pi I values for all 4 clusters, now what would be what would approximately be the pi I values for the model if you use the k dash value? In the previous question 3 we found out the value of k dash to be 3. So the question is, if we assume that the pi I values are equal with k equals 4, now if we merge these two clusters, this cluster and this cluster were merged in the last question, so k dash becomes 3 now, 3 clusters. Now what will be the approximate value of the mixing coefficients or pi i's? Shankarlal says A, Raghav says C. No, Shankarlal also says C. Okay. Pratik Tiwari says C. Correct answer is option C, 0.25, 0.25, 0.5. So for k equals 4 we have assumed equal pi's, that means each cluster contains equal number of data points. So pi I in that case is 0.25, 0.25, 0.25, 0.25. So because for a given cluster, if for the ith cluster, pi I represents the fraction of data points that belong to that cluster only. So if all the 4 clusters contain equal number of data points, so each will contain 0.25, 0.25, 0.25, 0.25 data points. So basically 25% of the data points each cluster will contain. Now in question 3 we have found out the answer of k dash to be 3. So we merged these two clusters because these two clusters are very close to each other, and even if we merge these two, it would still represent almost similar density estimation for GMM. So now if we merge these two, k dash becomes 3, and so basically these two, so if this is the first cluster, this is the second cluster, this is the third cluster, this is the fourth cluster. So we merged cluster 3 and cluster 4 into one. So basically we merged these 0.5 and 0.5. So we can just add these two up. Now we have three clusters, so we would have three elements in this pi vector. 0.25, 0.25. First, for the first cluster and second cluster, the pi I values would be same, 0.25, 0.25, because we are not touching these two clusters. These two clusters remain the same, but we merge this third cluster and fourth cluster, so we add these two pi I values, 0.25 and 0.25, so this becomes 0.5. So 0.25, 0.25, 0.5. Now the cluster 3, which is a merged cluster by merging this 3 and 4, will contain 0.5 or the 50% of the elements. So that's why mixing coefficient for this third cluster would become 0.5 now. So this is how we can compute it, and the correct answer would be option C. Is there any doubt in this problem? Pratik Theory, do you want to ask? Yes. Yes. No, the it doesn't depend on the size. It depends on. I mean, we assume that the all the pi I values are equal for every cluster. So we have assumed that, but in different problems, pi I values will be different. But it has to sum up to 1, because you are dividing 100% of the data points among 4 clusters. So sum over pi I should be 1, but in this question we have assumed that each cluster would contain equal number of elements, or each cluster has equal pi I values. So that's why it will be 0.25 for each of the clusters. And so third and fourth, these two clusters also contain 0.25, 0.25 number fraction of elements. So obviously if we merge these two, we would end up with 0.5 elements in the merged cluster. So that gets reflected in this third cluster in case of k dash equals 3.
So this based on density of that cluster in previous that.
Yes. Now question 5, this is again on Gaussian mixture model. For a set of points given in these orange dots are points. Each orange dot is a point, so there are many such points in this figure. The density estimation of a GMM is given below. So the GMM has found out these two clusters. These two circular, it's not exactly circular, these are all elliptical contours that you can see. So it has found out two clusters from the data points. And what is the problem evident in this image? So if the GMM has found out two clusters, so is it fine, or is there any problem with this density with this clustering found out by this GMM model? So 4 options are: first option is pi i's are too big, second option is the clusters are not sampled from a Gaussian distribution, the GMM has not converged yet, and fourth option is there is no problem with the clustering found out by the GMM. Pratik says option B, which is clusters are not sampled from a Gaussian distribution. Shankarlal also says option B. Anyone else? Any other answers for this question? The correct answer is option B. The clusters are not sampled from a Gaussian distribution. So the GMM would always find out Gaussian shaped clusters like this. This is one cluster, this is the second cluster that GMM has computed. But the problem with this is that these orange points are the data points, and the data points are distributed like this. This is one cluster, this is another cluster. So these are certainly not coming from Gaussian distribution. If the data points, if they are coming from Gaussian distribution, it would be sampled like this in a circular fashion or an elliptical fashion. This might be one cluster and this might be another cluster, so that we can use Gaussian distribution to approximate them. But the data points are not distributed according to Gaussian distribution. These are shaped like banana, so the points are, there are no points within that, so that it can create a circular or elliptical contour over that. So because of that, this clustering found out by GMM is not correct. So option B is the correct answer. The data points are not distributed or sampled from a Gaussian distribution. The next question is again on the same diagram. So what can be done to get a better fit or to get a better clustering using GMM? Four options are there. Increase the value of k. Previously it used two clusters, so k equals 2 in case of the previous question. Now in the next question, the first option is by increase k, by increasing k whether we can get a better fit. Second option is use a better initialization. Third option is learn for more iterations, and fourth option is there is no problem with the fitting of the clustering. Pratik Tiwari says option D. But we have already found out that there is a problem, right? So the last question was, what is the problem evident from that image, that the points are not coming from Gaussian distribution. So option D cannot be correct, that there is no problem. So there is a problem with the GMM model that was used in the previous question. Sankarlal says A and B. So A is increase k and B is use a better initialization. And Raghav says A. Atyam Naga Venkateswarlu says option B, which is use a better initialization. Anyone else? No, I mean in the previous JMM it has found out these two clusters, but can we do better so that we find out not these two clusters but some other clusters, so that it fits the density of the data points better.
But that better is not the right question. Is it? Question of these two connections.
Okay, so the correct answer is increase k. So I will tell you what happens if we increase k. So in the previous question, two clusters were used only. So if we increase the number of clusters, so now it will be able to find out these. I mean, each cluster would be a Gaussian distribution in case of JMM. We cannot change that. In JMM, each cluster would be a Gaussian. So if we increase the k values, it will find out the small clusters. So now the number of clusters are not 2. We cannot find out a better JMM fit with 2 clusters, obviously, because this data distribution is much better suited for density based estimation, density based clustering models. But if we increase the k values, it will find out these small clusters. So now the number of clusters are much more, but it's better than having only 2 clusters where each cluster was Gaussian distribution and points are not at all Gaussian distribution, coming from Gaussian distribution. So if we create those small clusters, now we are able to fit the data points almost perfectly. So by increasing k, we can get a better fit. But if we want only 2 clusters, we cannot do that using GMM. With only 2 clusters, we can get only, this is the best that we can get from GMM with only 2 clusters. But if we want to get more than 2 clusters, then we can get better by creating small clusters from each of these clusters. So this is the GMM clustering with k equals 8, and these are the contours that you can see. Yeah, these are the contours that you can see. So this is one cluster, this is another cluster, this is another cluster, this is another. So 4 clusters, and then this is the 5th cluster, 6th cluster, 7th cluster, 8th cluster. So now instead of 2 clusters, we have to create 8 clusters to better fit the data points. But it's much better than having 2 clusters where the points are not at all coming from Gaussian distributions and the 2 Gaussian distributions were kind of overlapping on each other. That was not fitting the data point at all. But with 8 clusters, we can better fit the data.
And like if you compare it with other clustering previous scan,
Yes.
how we say if this one is the problem
Uh,
of the
in my opinion, DB scan would be much better because it would create only 2 clusters. So this would be one cluster and this would be another cluster using DB scan. And so yeah, so in DB scan or any density based estimation, even hierarchical single link hierarchical algorithm would also be able to find out these 2 clusters. But GMM cannot work well with only 2 clusters because each cluster is assumed to be coming from Gaussian distribution. So for GMM, if we take more higher value of k, then it does better. It creates those small clusters and data points or densities are much better represented here. Now question 7. Given n samples x1, x2 to xn drawn independently from an exponential distribution with unknown parameter lambda. So lambda is the unknown parameter of the exponential distribution. find the MLE estimation of lambda. The MLE is maximum likelihood estimation of lambda. Pratik Tiwari says option C. Okay. So the exponential distribution, the PDF or the probability density function for the exponential distribution for a given point xi with parameter lambda is given by lambda to the power lambda into e to the power minus lambda xi. So this is the exponential distribution for the data point xi with parameter lambda. This is only for one single data point xi, and there are n data points that are randomly independently drawn, and you have to find out the MLE estimation for the unknown parameter lambda. Raghav also says option C. Okay. Has anyone else computed the answer for this question? Pratik Vinod says C for exponential distribution. So the correct answer is option C. So how can we compute this? For a given data point xi, for a single data point, the density function looks like lambda e to the power minus lambda xi. So basically we have to compute the likelihood. So if we represent likelihood by L of lambda, because we want to find out the maximum likelihood estimation value of lambda for x1 x2 up to xn points. So this log likelihood is simply product of the individual density function values I equals 1 to n. So for every point we compute the PDA values and we multiply all of them together. So it would become lambda e to the power minus lambda xi I equals 1 to n. So this next we will compute the log likelihood. So generally we use natural log. So the natural log of the likelihood function would be, so because of this log, this multiplication would become summation. So summation of log of lambda e to the power minus lambda xi I equals 1 to n. So now we want to next after that we will take the derivative of this log likelihood with respect to lambda, and we will set it to 0. So basically we will take the derivative of this with respect to lambda and we will set it to 0, and from that we can find out the value of lambda. So the derivative value would come out to be this n by lambda minus summation over xi xi equals 1 to n, and we'll set it to 0. So from this equation we can find out the value of lambda, which would be n divided by summation over all the data points. So this is how we can compute the MLE estimation value of lambda. So first we have to compute the likelihood, that is simply the summation product of all the PDF values for all the data points, and then we take the natural log of that. So it would become natural log for individual points as well. So natural log, so in case of log the product would become summation. Now we will take the derivative of this log likelihood expression with respect to lambda, not with respect to xi, with respect to lambda, because we want to estimate the value of lambda, and then set it to 0, and from that equation we can find out the MLE value of lambda. Now question 8 is also very similar. Now for Poisson distribution, instead of exponential distribution, now you have to find out the MLE estimation of the lambda, parameter lambda of the Poisson distribution. So Poisson distribution, the PDF is and the unknown parameter is again lambda, and it is I think lambda into e to the power minus lambda xi divided by xi factorial. This is the PDF of the Poisson distribution. Now for this Poisson distribution you have to find out again you have to find out the MLE estimation for lambda. This xi would be here. So if I write it correctly, it would be lambda to the power xi by xi factorial e to the power minus lambda. Pratik Tiwari says option D. Pratik Vinod says option D. The correct answer is option D. So both of you have written correct answer in the chat. So this is the PDF function for the Poisson distribution. Again we will compute the likelihood L lambda for all the data points. So it would be product of fxi parameterized by lambda I equals 1 to n. So now if we take the product for each of the data points, it would be lambda to the power x1 plus x2 up to xn divided by x1 factorial, x2 factorial up to xn factorial, and this should become e to the power minus n lambda. And then we have to take natural logarithm of this whole thing. So ln of L lambda would be, so for this part for the ln it would become minus n lambda plus for this numerator lambda to the power x1 plus x2 up to xn, we will get x1 plus x2 up to xn ln lambda, and then for the numerator we will get minus ln of x1 factorial, x2 factorial up to xn factorial. We have to take the derivative of this with respect to lambda, so we have to compute derivative of this with respect to lambda and set it to 0. So if we take the derivative with respect to lambda, we will get so for this we will get minus n. For this part we will get x1 plus up to xn divided by lambda, and for this part the derivative value is 0, so we will set it to 0. Now from this we will get lambda equals x1 plus x2 up to xn divided by n. If we switch the sides we will get lambda equals this. So lambda equals summation over xi I equals 1 to n divided by n, which is option D. So this is how you have to calculate. Now question 9. Suppose we have a Gaussian mixture model of 3-dimensional data. So each data point is 3-dimensional with 4 components. So components basically means number of clusters or the value of k. So this is nothing but value of k, and this 3 is the number of dimensions in each data point. And we use a model with full covariance matrices. How many parameters are there in the GMM model? So the information that are given are 3-dimensional data points and 4 components in the GMM model, and we are using full covariance matrices. Then how many parameters should be there in that GMM model? So the parameters of the GMM model are mu, sigma and pi. For any GMM model, these are the three different parameters. Each of these are vectors. Mu would be a vector, this covariance sigma is a matrix, and pi. So there will be many such mu, and there will be many such sigma, and there will be many this pi. Pratik Vinod says 60 and Pratik Tiwari says D. So both the answers are option D. Raghav says A, which is 30. Sankarlal says 40. We have got many different answers in the chat. A, B, D, these are the three different options that I have got in the chat. Sankarlal now says 30. Okay. So as I already discussed that these are the three different kinds of parameters in any GMM model. So for ith component or the ith mixture, we will have mu I, sigma I and pi I. So for the ith component, and there are four such components. So if we compute for one component, we can multiply it by 4. So how many parameters would be there in mu I? So in mu I, so each data point is 3-dimensional. So certainly there would be the mu is the mean of the data points in that component. So mu would also be 3-dimensional. So the number of parameters in mu I is 3. Then sigma I, so this is a little complicated. So sigma is the covariance matrix. So if the data points are 3-dimensional, the covariance matrix sigma I would be 3 cross 3 square matrix, because this is a covariance matrix. But as this is a covariance matrix of the data points within that component, so this would be a symmetric matrix. So we don't need to keep track of all the 3 cross 3 or 9 parameters from that. We just need to know one half of the covariance matrix, including the diagonal points. We also need the diagonal points, obviously. So we don't need 9 parameters, we just need one half of that, including the diagonal. So that would be 3 into 3 plus 1 by 2 is just one half of the covariance matrix, including the diagonal points. So it would be 3 into 4 by 2, which is 6. So for sigma I, the number of parameters is 6, which is this one half of the covariance matrix. And finally we need pi I. So for one component, pi I is just a scalar value, which is the mixing coefficient. How many data points are there out of all the data points? So this value ranges from 0 to 1. This is just the fraction of data points that belong to the ith cluster or component. So this would be the only scalar value 1. So 3, 9 and 1. So for For the ith component, we have 3 plus 6 plus 1 equals 10 parameters, and there are 4 such components. K equals 4 here. So we have to basically multiply 10 by 4 and we will get 40. So 40 is the correct answer, option B. Yeah, this is how you have to calculate. 3 different types of parameters are there. For every component, we will have same number of pi, mu I, pi I values, or sigma I values. So if you compute only for one component, you can just multiply it by the number of components at the end. So pi I is 3-dimensional, so there are 3 parameters in that. Sigma is a matrix, is a covariance matrix, but we just need one half of that. We don't need to keep track of the whole matrix because it would be a symmetric matrix. And then pi I is just the mixing coefficient for the ith component. It would be a fractional value from 0 to 1. So this is only this would only be a scalar value 1. So for ith component, we will have 3 plus 6 plus 1, 10 parameters. So 10 parameters for one component. For 4 components, we will have 40 parameters.
Value only covariance value 1.
Which one? This pi I are you talking about?
Yeah. Yes. You can do 0 to 1 anything.
The number of parameters in that pi I value ranges from 0 to 1. But the value is only one parameter. It's from 0 to 1, only one parameter we have for that. Either it's 0.1, 0.2, 0.3, 0.25, whatever, but it's just a single value, one parameter that represents the pi I. We are computing number of parameters in each of these, mu I, sigma I, pi I. Is there any other doubt in this question? So the answer would be B, 40. In question 10, which of the following correctly describes the difference between EM for mixture of Gaussians and K-means? And there might be multiple correct answers in this question. So the main difference between EM for mixture of Gaussians and K-means. So these are the 2 different algorithms for clustering. So first option is K-means often gets stuck in a local minimum while EM tends not to. Second option is EM is better at capturing clusters of different sizes and orientations. EM is better at capturing clusters with overlaps. EM is less prone to overfitting than K-means. Pratik Tiwari says B and C. Shankar Lal says B and C. The correct answers are B and C. These are the 2 correct options. So So first option says that k-means often gets stuck in a local minimum while EM tends not to, which is not true. EM also sometimes might get stuck in a local minimum, or in case of EMM we want to maximize, so it gets stuck in a local maximum point, which we have already discussed in the first question, that it is very it's a known problem for that it can get stuck in a local maximum point EM, and k-means obviously sometimes get stuck, so this option is not true. Second option is EM is better at capturing clusters of different sizes and orientations, and this is right. K-means only finds out clusters which are spherical in shape, but in case of EM, though it uses Gaussian mixture models, but because of this mixing of different Gaussian distributions, it is able to capture clusters of different sizes also, not just spherical clusters. It can also find out clusters of other shapes and sizes. And third option is EM is better at capturing clusters with overlap, which is certainly true. So the EM for mixture of Gaussians finds out soft clusters, whereas k-means is for hard clusters. So if two clusters are overlapping, in that case EM would be much better. It would find out the mixing coefficients and the other parameters of the Gaussian mixture model to find out how much overlap is there. So it finds out the soft cluster, so that's why option C is also correct. And the last option is EM is less prone to overfitting than k-means, which is not very evident from the algorithm. It depends on the task or the distribution of the data points. We cannot say that it is less prone to overfitting. So the only correct options are B and C. So these are the two correct answers. So these were the problems that I wanted to discuss in this live session. Now if you have any questions or queries, you can ask me. Raghav says, why not option A? So k-means gets stuck in a local minimum, even EM also sometimes gets stuck in a local minimum. It says that while EM tends not to, which is not true. EM can also get stuck in a local minimum. Any other questions? If there are no other questions, then we can end this live session here. Okay, Pratik is saying EM algorithm minimizes a lower bound of the marginal likelihood P d theta. True or false? Is this question given in the assignment? If it is in the assignment, I cannot answer that. If it is given in the assignment, the deadline is not over yet. So in that case, I cannot answer that right now. Okay, thank you everyone for joining. We will again have a live session next week.